All right, here we go. So what we're going to look at today is something called the Basel problem, named after Euler's hometown because he was first guy to solve this thing. So what we're going to do is we're going to look at the sum from 1 to infinity of 1 over n squared. And spoiler alert, this turns out to be pi squared over 6. All right, so let's figure out how to do that. So in our book, the book kind of recommends we use this crazy function. So we're going to look at this function pi times the cotangent of pi z all over z squared. And we look at this one because it's got some nice residues. It's got some nice singularities and that sort of thing. So using this function, we're going to kind of use this nifty little sum theorem we have here. So let's take a look at this one. Basically, this sum says we're going to take the sum from negative infinity to positive infinity of some function f of n. All right. This is going to actually be equal to the negative sum of the residues. So we'll say sum of the residues of this weird looking function of this pi times the cotangent of pi z all times our f of z, all right? And the f of z in this case is going to end up being our 1 over n squared. All right, so let's kind of see what happens with this. What we need to do is we're going to start with this crazy looking function again. So this pi times the cotangent of z. All right, what we're going to do is we're going to integrate this thing. All right, we're going to integrate this over some path gamma. All right, and this gamma, what we're going to do is it's a rectangle on this next page here. Forgive that watermark down at the bottom, but we're going to take this function that you see in red, and we're going to integrate it over this path gamma. It's kind of this rectangle, and it turns out that these are basically an integer plus 1/2, off of the origin, and then up top here, we're going to call these I times some integer n. So what we're going to do is we're going to take the limit of this thing as it goes to infinity. All right, so let's see what happens here. So this, if we take the limit of this function as our capital N goes to infinity, all right, what we're going to end up with is the limit over on this side, limit as n approaches infinity of this sum, capital N. All right, so we're going from negative n to capital N. Of our function f of n plus the residues. All right, and again, it's going to be the residue of this function here, of this pi times a cotangent of pi z thing. So that's kind of our strategy here. So if we look over at the left-hand side here, this integral turns out as n approaches infinity, in this case, let's look over here at this. These things, they get closer and closer to 0. So the farther and farther away we get from the origin, basically they're really starting to flatten out. So the idea is once we go to infinity, it's 0. So I'm not going to do a formal proof on that one in the interest of time here. So let's see here. We got the left-hand side is going to be equal to 0. And let's look at the right-hand side. So this is going to be the sum from negative infinity to positive infinity of this f of n, all right, plus our residues, all right, the residues of this pi cotangent. I don't want to keep writing that over and over, but all we have to do is just subtract that residue to the other side, and what we're going to be ending up with is the sum from negative infinity to positive infinity of this f of n, which remember is that 1 over n squared. That's going to equal our negative residue, and again, the residue of this pi times the cotangent of pi z function. All right, so that's kind of our strategy. Let's see what happens from here. Let's look at the residue of this function. All right, so what we're going to do is let's try to figure out what's going on here. Now, cotangent, real nasty Taylor expansion here. So the cotangent of z, all right, basically we have cosine over sine, so expand out cosine, expand out sine, divide the two, and then a whole bunch of simplification from there. So what's going to happen is this equals 1 over x minus 1/3 x minus 1/45 x cubed. all right, and then minus a whole bunch of other terms. We don't really care past, the third term, maybe even the second term, because we're looking at the residues. All right, so what we're going to have here is, let's look at the original. So pi over z squared times the cotangent of z. Of pi z. Cotangent of pi z. All right, this is going to equal, I'm going to take that pi over z squared. We're just going to throw that out front for now. All right, then let's see what happens here. All right, so look at the green one compared to the red one. What we're going to end up with is 1 over pi z. We got 1 over pi times z minus, we're going to have pi z over 3. All right, and then we'll take it to one more. That's going to give us pi cubed. Why not? Pi cubed over z cubed. Pi cubed times z cubed, all over 45 minus, a whole bunch of terms. And distributing in this pi over z squared. All right, let's see what that looks like. That's going to give us, well, those pi's are going to cancel on top and bottom, so we're left with 1 over z cubed minus, looks like that's going to give us a pi squared over, you got a z on top, 2 z's on bottom, so that's going to give us z. Oh, can't forget about that 3. All right, and remember, z to the negative first, that's that residue we're looking for. So if we just look at the coefficient on this term, we're going to get the residue. The residue is going to be equal to a negative pi squared all over 3. So that's going to be kind of nice, because remember, in that formula, it was the negative residue. So what's going to happen is those negatives end up canceling out. All right, so kind of circle back here. We're going to look at the sum from negative infinity to positive infinity of 1 over n squared. We said this equals the negative residue. So that's like a negative pi squared over 3, right? So those negatives are going to cancel out. All right, so one thing to notice, 1 over n squared. That's an even function. That's useful because this is going to be equal to 1 over negative n squared. All right, so what we can do now is I'm going to rewrite the sum, all right, from negative infinity to positive infinity. Let's rewrite that. I'm going to call this the sum from, we'll start at 1 and we're going to go to negative infinity. All right, 1 over n squared plus, now let's take the other side. That's going to give us a 1 to a positive infinity over the sum of that. What am I trying to say here? The sum from 1 to infinity of 1 over n squared. All right, this ends up equaling a positive pi squared over 6. No, it doesn't. It equals pi squared over 3. Sorry. All right. However, using kind of this fact over here, right, the fact that it's an even function, these two functions, they're essentially the same thing. So let's just combine them, right? We're going to say 2 times the sum from 1 to infinity of 1 over n squared. All right, this equals our positive pi squared over 3. All right, now let's divide away that 2. So our final answer, all right, and that answer that Euler came up with when he was like 6 years old or something, the sum from 1 to infinity of 1 over n squared equals pi squared over 6, which is our final result. Right, so all it took was using that crazy cotangent function and looking at the residues, and then it kind of all fell into place from there.